NMR spectroscopy is one of the most powerful tools for determining the structure of organic compounds. Unfortunately, at present, ChatGPT cannot solve the NMR by its own, which means we have to learn how to interpret them by ourselves. In this NMR Challenges series, we are going to learn how to interpret 1H NMR, 13C, 13C APT, and what is the difference between 13C APT and DEPT 135 NMR step by step. And we will start with the first with the easy task, and then we will go to the moderate, and after that we will solve the advanced NMR problems. Hello students, welcome back to my channel Dr. Vijay SSOC. So let's start today's NMR challenge. So here is our first NMR challenge. We are going to determine the structure of this organic compound whose molecular formula is C4H8O2. While determining the structure of this compound, we will learn how to calculate the index of hydrogen deficiency, how to interpret 1H NMR, and how to extract the informations from 1H NMR. And then we will see how to interpret 13C APT NMR and what is APT, and we will understand how it is different from 13C DEPT 135 NMR. So here is the proton NMR of this compound, which was recorded in CDCl3, and this signal is from the residual chloroform. And this is the 13C APT NMR of this compound. Before solving this problem, we should understand some steps, and we will follow those steps whenever we will solve such problems. So what are those steps? So here are those steps. First is the calculation of index of hydrogen deficiency. It is also known as degree of unsaturation, whose formula is 2C plus 2 plus N minus H minus X divided by 2. So here C is number of carbon atoms, H stands for number of hydrogens, N stands for number of nitrogens, and X is number of halogens. So this value gives you number of pi bonds or rings, or it could be both. If index of hydrogen deficiency is equal to 5 or more than 5, then we can blindly say that it has one benzene ring. And after that we will look 1H NMR. So from 1H NMR we will see number of signals equal to how many types of protons are there. Then we will see splitting patterns, which will tell us about number of neighboring protons or substitution patterns on the benzene ring. So we know that splitting pattern follow n plus 1 rule, where n stand for number of adjacent protons which are equivalent. And then we will also understand some chemical shift values of the protons, which will give information about shielding and de-shieldings of the protons. So I would like to ask you to remember some of the values. For example, from 1 ppm to 2 ppm, you usually get the aliphatic protons. And the most important value is when carbon attached to the ketone group, then the proton comes from 2 to 2.6 ppm. And it is almost same for the methyl attached to the benzene ring. When the proton attached to the acetylene carbon, which is sp hybridized, then its value comes between 2.5 to 3 ppm. The most important value is also when oxygen is attached to the methyl group, then it comes from 3.5 to 4.5 ppm usually, or when it is attached to the nitrogen, then it comes slightly lower from 3 to 4 ppm. We should also remember that the hydroxy and NH2 are acidic protons, therefore they are exchangeable, and it shows variation from 1 to 5 ppm. So these values are not fixed. And then we should also remember vinylic hydrogen usually showing between 4.5 to 6 ppm, and sometimes it overlaps with the aromatic protons, and then it creates confusion. So aromatic protons comes from 6 ppm to 8.5 ppm. We should remember aldehyde protons comes after 9.5 ppm to 10.5 ppm, but carboxylic acid always shows the broad signal after 10 ppm to 13 ppm. So these are the some values which we should remember. Then only we will manage to solve the structure of the compound. So first step is index of hydrogen deficiency, second is seeing the 1H NMR, and after that looking the 13C APT. So APT stand for attached proton test. This gives signals for all kinds of carbons, unlike 13C DEPT, because in 13C DEPT NMR you can't see the signal for quaternary carbon. So for quaternary carbon you don't get the signal in 13C DEPT NMR, but in case of 13C APT you can see the signal for quaternary carbon also. So you can see all types of carbon present in the molecule, and it can distinguish between methine CH and methyl peaks, which are 180-degree opposite to quaternary carbon and methylene. So quaternary carbon and methylene will give upward peak, while CH and CH3 will give downward peak. And we should also remember some of the 13C chemical shift value. For example, we should know that primary carbon, secondary carbon and tertiary carbons comes in the shielded region from 0 to 55 ppm, or usually it shows up to 40 ppm depending upon the electron density on the carbon atom. But if it attaches to the oxygen, then it usually shows signals from 50 to 70 ppm. When it is attached to the nitrogen, then it comes from 40 ppm to 60 ppm. Acetylene carbon shows signal between 70 to 90 ppm. Benzene shows wide range of signals from 110 to 170 ppm. We should remember the signals for those functional groups. For example, ester comes from 165 to 175 ppm, and amide also comes 160 to 175 ppm. Carboxylic acid is slightly higher, 175 to 185 ppm. Aldehyde carbon usually shows signals in highly deshielded region with low intensity, and ketone is also same. Okay, after knowing these values, we can start solving our problem. So let's move to the problem. Now we are going to follow each step one by one. So first is calculating the index of hydrogen deficiency. So what is the formula? 2C plus 2 plus nitrogen minus halogen divided by 2. So we have 4 carbons plus 2, no nitrogen, 0 nitrogen, 8 hydrogen and 0 halogen divided by 2. So it is giving 1. So this one could be 1 pi bond or 1 ring. Now we will look 1H NMR. So how many signals are there in 1H NMR? A, B, C. These signals belongs to the residual chloroform signal. So there are 3 signals. So 3 signals means 3 types of protons. Okay, so the signal A is coming around 1.4 ppm, which is triplet. You can see that 1, 2, 3. So this is triplet, and integration value is 3. So it corresponds to the 3 hydrogen. This 3 hydrogen implies that this could be methyl, and this triplet means if you apply n plus 1 is equal to 3, so n is equal to 2, it means it has 2 neighboring hydrogen. So it could be possible that there is CH2 which is attached to the CH3. So this is information we are getting from this 1H NMR. And let's look at the signal B. Signal B is coming around 2.07 ppm, which is singlet, and this integration value corresponds to 3 hydrogen. So this indicates that there is CH3 group, and this CH3 group doesn't have any neighboring hydrogen, so no adjacent hydrogen. So now look at the signal C. So signal C is quartet 1, 2, 3, 4. So it is quartet which is coming around 4.2 ppm. Let's say it is around 4.2 ppm, and quartet integration value coming to 2 hydrogen. So this 2 hydrogen indicates that it could be CH2, and its neighboring value would be 3. So it means it could be CH3. So hence we can say that this CH2 is attached to CH3. So this information is comply with this information. So we are 100% sure that the compound contains ethyl group. Now look at the carbon NMR. From this carbon NMR, we can see that this value, which is around 171, is usually correspond to ester, amide, and carboxylic acid. But it could not be amide because we didn't see NH2 proton in the proton NMR. It could not be acid because we didn't see hydrogen in the NMR. But it could be ester because it also satisfied our molecular formula, because we have 2 oxygen atom in the molecular formula. So it has 1 ester group. So now we have following information that the compound has 1 ester group, 1 methyl group, and 1 ethyl group. If you combine all these 3 fragments, then there are 2 possibilities. First is that CH3 is showing the singlet, so it is attached to this carbon which doesn't have any hydrogen, then oxygen, and after this CH2, CH3. This is the first possibility. And the second possibility is that this CH3 is attached to oxygen, then CO, after that CH2, CH3. Now here it is important to have knowledge about chemical shift of 1H NMR. So if CH3 is attached to the keto, so it usually comes around 2 ppm, and this one attached to directly to the oxygen, so it comes around 4 ppm. And in this case, this CH3 which is directly attached to the oxygen will be around 4 ppm, and this CH2 will be around 2 ppm. If you look at the 1H NMR, then you can see that this CH3 is coming around 2 ppm, and this CH2 which is quadrate, this is triplet, and this is singlet. So the quadrate is coming around 4 after 4 ppm. So we can clearly say that the given 1H NMR and carbon belongs to this molecular structure, not this one. Now let's look at this 13C APT also. This value will be for CH2, and these downside signals are for CH3 or CH methane proton. Since we don't have any methane, so both belongs to CH3. So both are belonging to CH3. So let's look, we have 2 CH3, yes, 1, and this is 1 CH3, this is another CH3. So yes, we have 2 CH3, we can clearly see downside signals are belonging to CH3, and we have 1 CH2. Yes, this is 1 CH2, and this is the ester signals. So hence we can clearly say that the correct structure of this molecular formula is this one, not this one. I hope this is clear to you. If you have any doubt, you can ask me in the comment box. So now here is a question for you. This is the molecular formula, and this is the 1H NMR and 13C APT NMR. Use all those steps and try to determine the structure of this compound, and we will disclose the structure of this compound in the next video. But if you manage to solve, then send me in the comment box the correct structure of the compound. So we will see you in the next video, and please Don't forget to subscribe my channel because it motivates me to take out time from my busy schedule and make such types of YouTube videos for the students. Thank you very much.